this third video, we look at how to set up the production strategies that you wish to compare. Go to the sheet S1-Standard to set up your standard culture plan. There are just 4 numbers here that you can change. The first is the average weight of the fry or fingerlings that you stock. The minimum size you can specify is 1 gram. The model is not intended to be used for very early rearing. Also note that the model has only been tested against data from a growth trial from 40 to 500 grams, so may be less accurate for smaller and larger fish. The accuracy will also decline the longer the growth period. You should then specify the number of fish you stock per cubic metre of cage volume. If you have not previously calculated this, divide the total number of fish that you stock into a cage by the cage volume in cubic metres, which is calculated in the 0-Start Here sheet. You are then asked to specify the number of days between stocking and harvesting the fish. If you have a normal number of days, then you can enter that here. If you plan to grow the fish to a certain average size, note the average weight figure shown adjacent to the days to harvest. As you increase the days to harvest number, the average harvest weight figure will also increase. Adjust the days to harvest number until it predicts your target harvest weight. This section also shows the average temperature and the cage dimensions, which can be adjusted on the 0-Start Here sheet. The final data element that you can adjust on this page is the days between harvesting and restocking. The spreadsheet firstly gives you information about a single culture cycle in a cage, but then also extrapolates that to an annual estimate, assuming that you keep repeating the same pattern with just a break for cage maintenance, etc. For instance, with a cycle length of 137 days and 10 days for maintenance, you could run 2.5 cycles per year. That's 365 divided by 137 plus 10, which equals 2.6 in each cage. The remainder of the sheet provides calculated data about each cage cycle and then multiplies this by the cycles per year number to give data for the cage over a full year. This sheet essentially shows the results of a growth model, which depends on a number of key variables that we will examine in more detail in later videos. You will see there is also some financial analysis here. This is quite basic, just considering income from sales and the 2 major cost inputs, feed and fry, including the cost of financing them, e.g. through interest payments on an overdraft. The accompanying charts summarise key information such as the expected growth of the fish and corresponding feed used, the expected distribution of harvest fish by weight category, and a breakdown of major operating cost categories and income. The first pair of charts, at the top as they are the most important, show the main operational costs, fry and feed, compared with sales income and gross operating margin, i.e. the value of sales less fry and feed costs for a single cage cycle. If sales income exceeds the cost of feed and seed, the first chart shows the cost of fry and feed separately, with any margin above these. If the cost of fry and feed exceed the expected sales income, the operation will make a loss, and this is shown by the bar extending below the 0 line. The sales income is the sum of fry, feed and income less fry and feed. The second chart combines fry and feed costs, but also shows the 3 main indicators, sales income, fry and feed costs and surplus margin, side by side for comparison. Again, if there is a loss rather than a surplus, this is shown below the 0 line. Below the summary financial information are the biological performance charts, growth and mortalities. These are both combined charts with biomass shown as bars with a scale on the left y-axis and the second dependent variable shown as a line with the scale on the right. One of the most critical variables is the price per kilogram that can be attained for different sizes of tilapia. In general, larger tilapia are more expensive per kilogram. The next chart shows the expected distribution of size grades within the harvest, based on a normal statistical distribution, and the corresponding contribution from the sales of each size grade to total income. The spread of sizes is adjusted in the model by altering the value of the coefficient of variation in the zero start here sheet, but we will cover that in more detail in another video. The final chart shows the increasing stock density over the culture cycle in kilograms of biomass per cubic metre of cage volume, and the pattern of feed consumption, with an adjacent table indicating expected quantities by feed type and grade. Try adjusting the key variables on this sheet, i.e. increasing or decreasing the production cycle length or the start weight and initial stock density, and see how the results change. The strategy sheets S2-double and S3-short are in exactly the same format as the first sheet and can be used for any production scenario that you wish to try. However, by default, each of these sheets are set up to replicate the trials that were carried out at Victory Farms in Kenya. Taking the S2 double sheet, for example, the same culture cycle is used as the standard strategy, but double the number of fish are stocked at the start. This results in a larger harvest, but somewhat smaller average size fish. The costs are much higher with this strategy, and also the risks, but so is the potential margin. Note that the stock density and daily feed amount are much higher than with the standard scenario. This is likely to lead to poorer water quality and risk of disease, which cannot be properly reflected in the model, so this type of adjustment to the model should be used with care. In the S3-short scenario sheet, the double stocking rate has been maintained, but the culture period has been reduced to keep within similar stock densities to the first standard scenario. This leads to a harvest of smaller fish at lower value. If you compare this with the standard strategy on the previous sheet, you'll see that the margin obtained falls as a percentage of total turnover. However, the risk of serious losses are reduced by shortening the culture cycle, and the fish may be easier to market locally. It also means less financial outlay before income can be realised, i.e. better cash flow. The final strategy, S4-partial harvest, is more complex as it assumes an interim partial harvest of the fish that are initially stocked. For this strategy, you need to specify the number of days to the first harvest and what percentage of the fish will be removed at that stage, as well as specifying the total culture days. As with the other strategies, you can directly monitor the predicted average weight for the number of culture days specified. You can also check the calculated data below for maximum stock density. The calculations are divided into sections for the first harvest, the second harvest, the combined harvest, and then the extrapolated annual totals. The growth chart shows the continued increase in average weight, but a substantial drop in biomass when the first fish are harvested. In addition to contributing to cash flow, this early harvest also prevents the stock density from increasing beyond reasonable limits. The cumulative mortality chart now shows the additional mortalities following the interim harvest. The size at harvest chart is now bimodal,
reflecting the combination of the two harvests. Separate charts are available on the Growth-4-Model 4 sheet. Financial charts show the results for combined first and second harvest, and then separate charts for the first and second harvest. This strategy does not produce as big a margin as the double stocking strategy, but does maintain a more reasonable stock density and provides some interim cash flow and a wider range of fish sizes, perhaps for different markets. The next step is to consider combining these strategies, but we will do that in the next video.